Good day, welcome to my talk, Using Search Effectively in Taxonomy and Correctly Modeling of Your Domain in Elasticsearch. My name is Renzo Gambone, I'm from Montevideo, Uruguay, and I've been working over 4 years in Xmartlabs as a machine learning engineer and backend developer. I have worked on computer vision, employing cloud and edge devices, as well as on NLP, particularly oriented to entity search. We'll start by showcasing the problem and its difficulties of entity search. Then we'll see why it makes sense to tackle those issues with Elasticsearch. After that, we'll see some examples and what to take into account when tackling said issues. And lastly, we'll be close with some examples and lesson learned. The first thing that comes to mind when thinking on the word taxonomy is the scientific classification on species, and not much more. But in reality, a hierarchical model with complex relationships between its entities has a lot of applicability in our line of work. Any type of search in a catalog can be done through modeling it as a taxonomy. It also adds logic and semantic meaning to our data, which improves its navigability. Maybe an elaborate search for species doesn't make sense if the users are scientists that know the exact name for everything they are searching for. But that's different in domains where the user is not an expert on the catalog. For example, a clothing shop. Clothes can have multiple fields. One can be their type, such as a blouse, a skirt, trousers, dress, shoes, sandals. They can also have a descriptor, such as a color, a pattern, or a texture, and they can also have a material, like denim, cotton, or lace. Clothes are also taxonomic. So there are many kinds of footwear. One of those can be sport footwear, such as running shoes or soccer cleats, whereas there can also be sandals, and flip-flops can be a type of sandal. So for this presentation, we'll center the examples around type, but all these concepts can be applied to any of these attributes and more. For the first examples, this will be our catalog. And the most intuitive strategy is to search for what the user wrote. An exact match strategy is analogous to searching for a value in a list or a database. There is a particular value that we are searching along our collection. So when we search shirt, we look for that specific value. This type of search is easy to implement, and if our users are experts in the domain, it should work for most of the cases. But language is very complex, and we may use a different name to refer to something, and our catalog may be partially incorrect. So here, in the example here, looking at the illustrations, we can see a raining coat, and we can see that it has a hood. Thus, in our catalog, we have an item for a shopper looking for a hooded raining coat. But with an exact strategy, those values differ, and the match fails. So, and also the same thing happens when a user searches for something too broad. The catalog has many shorts, but none of those is named just shorts. So the next step is to shift our strategy to a partial match. Rather than searching for a specific value, we have a set of sub-values, words in this case, and we want to match those with entities in our catalog by intersecting with a superset or a subset of the search values. Now, even with the hooded indication, the search matches. The same also happens when the search term is a superset, such as in the case with shorts. But what happens when a user makes a typo? The word sorts doesn't appear in our catalog, so the match fails. We know in the language that if someone is searching for raining, it makes sense to match with the word rain, such as in raincoat. But our current search strategy doesn't know our language. It only knows values. It also doesn't know our domain. We know a lot of vocabulary in the context of clothing, such as that beanie is the knit cap we have in our catalog. However, our search strategy doesn't know this. And with cases that can be more complex, if the user searches the word jacket, the search will match, right? We have a jacket right there on the catalog. Yes and no. We found a jacket, but a parka is a type of jacket. It is under that taxonomy, and that result doesn't match. So, our search strategy is not enough. Somewhere we must add logic of the language and of our domain, clothing in this case. Our first idea will be to model that into the data. Every item knows all its synonyms, has associations all modeled into our database. However, this will increment how much we are storing and requires maintainability to changes and any data to fix any error that can be in the data. So that is not good. What makes more sense is to add the logic to our program, but if we add it directly to code, it can be really expensive. We might require to make multiple queries, we might require to increase the complexity of the queries, and all of that will cause an increased query time. So here's where Elasticsearch comes in. I think all of you know Elasticsearch, so I'll be brief. As a search engine and database of knowledge for our taxonomies, we can see many benefits in using it, such as having a high-level interface to write and execute complex searches already developed, tests, and ready for us to use. Not only that, but it has tools that are specifically designed for the processing of attributes and analysis of our language, which we'll cover later. It also has good execution times because it is optimized for searching for text. And there are a plethora of other benefits, such as that we can declare schemas for our entities and they can be related with our entities. It has open code, scalability, many options for hosting, so it makes sense. Let's see how now to implement this model on Elasticsearch. First, we'll have to translate the example to a model, to an schema. As I mentioned, we'll focus on the type attribute, and looking at the code, we see that we have the type attribute in 3 places. One is type raw. This field will store the raw value of our data without any type of processing. We also have a type stemmed attribute, and we see in the code that it runs a basic analyzer of the language, default analyzer, which we'll soon see. And lastly, we have a type analyze attribute that says it runs a search analyzer, so it runs in search time, and runs an analyzer more specific for the clothing context. So, this analyzer is the one you get when you initialize an analyzer for the English language. An analyzer can be thought of a processing pipeline for a field. This one here runs at index time, transforming the loaded data, and at search time, transforming the data in the searches. Its steps are: first, it tokenizes a sentence by splitting words by space. Then it transforms that data into lowercase. Then it removes common words of the language, stop words, such as articles. Then it applies stemming to convert words to their root by removing plurals, conjugations, and this is what helps us go from raining to rain. So all of these steps will help us in the problem of actually understanding the English language. Then there is the custom clothing analyzer. So the first thing of this analyzer is that it has this exact same behavior as the previous one. It does tokenization by space, it does lowercase, removes stop words, does stemming, all that. But it also adds 3 special filters to the pipeline. The first is a keyword filter, which marks words not to be processed in the stemmer. In this domain, for example, we don't want leggings to be changed into leg. Also, it adds a custom stop word filter, which allows us to declare words we wish to ignore in searches. This can be words specific to our domain. So if they are searching in a clothing catalog, maybe the word today, change, or purchase doesn't add that much information in identifying the product they are searching for. And lastly, but not least, we have a synonyms filter that allows us to establish relationships between words for equivalences or for a preferred canonical. So we can say that jacket and parka are related, shoes and footwear, and we can also add knit hat as a canonical for beanie or toque, another synonym. This analyzer, as I mentioned previously, runs in search time, so it doesn't affect stored values in the database, which is great, since we can update our clothing vocabulary without having to reindex data. Let's see now how to query our model. Looking at the following query, we see that it has a should with 3 Boolean clauses. So each of these can match with results, and the more that match, the higher the search score. And we can also see that the same search term is searched on all clauses, so long skirt for this example. The 3 clauses differ on their boost, scoring higher for terms that match with type raw, then with type stemmed, and lastly with type analyzed. This will help us with the sorting of the results. We want to see first the results the user wrote, if they exist, rather than first showing all our synonyms or related clothing. Also, every term has a fuzziness value, which allows matching with values that differ in up to 1 character. It can be 1 character less, more, or different. And this will help us alleviate the problem with the orthographic errors. Now, we can see in this example that fuzziness solves our typo issue. We are getting results. However, now they are less specific. The word shorts may be a type of shorts, but also a type of shoes. All of these words differ on a single character. We can also appreciate how partial match affects the Elasticsearch score, as the other 3 results have less score for having an extra word, but the score the word shoes and shorts is the same. Now, searching for rain returns the expected raining coats. And this also solves our synonym issue. Searching for beanie returns the knit hat. And not only finds both jacket and parka, but remember that we designed the query so that it scores higher with the exact search terms. So jacket has more score than parka. And the opposite will have happened if the user has searched for parka. Jackets will be shown, but after all the parkas. But what happens if the user searches for something that does not exist in our catalog or synonyms, such as workout? The truth is that a classic static model will work for a lot of cases, but it requires a lot of time and effort to have an exhaustive model, presuming that's even possible. So here is where we can add some machine learning tools. As another improvement, we can complement our model with searching in vector spaces through word embeddings. Presuming that we have a pre-trained model that receives a sentence and returns the semantic representation on a vector space, we can run the model on query time to get the embeddings for any search term, so a vector representation of that search term. And in our data, we can add a new field, type vector, which will store the previously processed embedding for that value. Through vector search strategies, such as cosine similarity, we can identify similar elements in our domain. But these results might have some noise, especially if our model is only trained on language and hasn't received any additional training with explicit examples of the clothing domain. It might, for instance, make antonyms strongly related to each other, as grammatically they can usually be substituted for one another. But I think it certainly brings value, so let's see how to integrate into the search as fallback. This will be our last resource. After having added all the embeddings to our data and modified the query script to add a new clause that applies cosine similarity with the result of embedding the search term, we can see now, when we search for workout, we see how the word workout relates to all our catalog, being sorted in closest relationship with highest score. And looking at the results, we see that workout clothing such as tennis shoes, swimming shorts, and running shoes has the best score. This, however, doesn't generalize that well, as dresses and strap sandals have a higher score than shorts. All these results were obtained with a model that was trained for the general language. It wasn't retrained for the clothing domain, and is a really simple model among all the embedding models that are out there. But we see that, at least for the first results, it's working decently well. And we can also see that all these results have less priority than the results from our static modeling. Now, searching for coats, we see the first results being raincoat. But we can also appreciate jacket and parka being up there. They are related, even though we didn't add a rule that classifies them as a type of coat. Then, if embeddings are that great, why did we lose all that time with making a static model? Because look at what happens with a general model when searching for workout pants. One would expect to see leggings on top, but that's not the case. The first results are strap sandals. This problem can definitely be solved by retraining the embedding model, but doing that will take time and effort. It will require processing time. It will require iterating and experimenting with multiple model architectures. And among other things it may require, that is having a curated dataset. But a good takeaway is that without having done any of this work, we were still able to complement our searching strategy decently well. It also adds an interesting relationships in between words, in which rather than showing no result, our search can now show similar results, such as a necklace if the user searches for ring. This isn't what the user searched, but it is related, as both are a type of jewelry. So this vector space allows us to connect entities that aren't synonyms or aren't strongly related words. To sum up, this solution makes our data smarter and distributes logic more evenly in our program. We saw how, with the aid of high-level functionalities, we were able to increase the accuracy in search, particularly tailored to the most common mistakes or errors that can happen when searching through a catalog. Also, analyzers are modular. They can be customized, they can be sorted, a new step can be added, or they can be replaced by any other analyzer. We also saw how this can be assisted by other NLP techniques, such as word embeddings, but also it can be assisted by entity recognition, such as rather than tokenizing by space, we can tokenize by entities we find on the text. It can also, in the case we were also searching for color and type of material, we could add a labeler that classifies the query as this is a color, this is a material, or this is a type. But I think the most important takeaway from this talk is that since we relied on high-level implementations, the development time of this solution was really quick. In just 1 or 2 weeks, given that we have the data of our catalog accessible, we were able to develop a really decently solid solution which can act as an MVP for our product. And this really contrasts with the approach of focusing on training the perfect machine learning model, which will require a lot of more of throughout study, labeling of our data, and all of this will push the functionality being available to our stakeholders or to public for an initial release. That is something we definitely can add later in the process. Of course, all this modeling has its downsides. The specific taxonomy rules have to be curated manually, at least to cover frequent searches, and the taxonomy is context dependent. If the domain changes and terms lose their meaning or gain new synonyms, those files should be updated. And in the clothing domain, that may be easy, but on a really technical domain, we may require having experts that know of their domain and the taxonomy on the catalog to make these rules. Thank you so much for your attention, and see you.